general relativity step by step. I'm going to draw a coordinate system, a general curvilinear coordinate system, and I'm going to draw the lines of constant x2. No, this is constant x1. There it is, and this is badly behaved. So that's x1 equals 0. This line here is x1 equals 1. That's x1 equals 2. That line there is x1 equals 3, and so on. And I'm going to draw the other coordinate lines in blue, like this, and this is very badly behaved, wibbly wobbly all over the place. And that's x2, and of course this corresponds to y, I guess, if you 2 equals 1, x2 equals 2, and so on. And of course these guys don't cross at right angles, and it's a mess. I'm going to define a scalar field. I'm going to go back to black. I'm going to define a scalar field. It's a scalar, something like temperature perhaps, or actually altitude on a map. And phi equals phi of x1 and x2, so it's a scalar field. Notice I'm casually flip-flopping the notation between phi being the function which maps a particular value of x1 and x2 to a particular value of the scalar, to a particular value of the temperature or altitude, whatever it is. And I'm using the same notation to refer to a function. And even that is slightly ambiguous because it's not quite clear whether these x1, x2 here are particular values of x1, x2, or if they kind of range over the whole set that they're allowed to range over. So I'm going to draw some contours. This is getting a bit messy, isn't it? These are contours. Black lines equals contours of phi. There they are, and here I am standing on. Let's just say that these are contour lines like on a map. Contours of altitude. Contours of altitude. So here I am. Actually, I'm going to change that. I'm going to be green. That's me standing there. I'll get rid of black me. Oops. Better put that line back in. There he is. Whoop. Yeah. Come on. There we are. And there's my friend standing there. And I'm standing there, and I want to know how much altitude I gain to get from point A to point B. There's my friend, and I want to climb up the hill and see him. So I'm interested in the change in phi, which might not be small, might be large. Big. I guess you could call it delta phi if you're bothered about that. And delta phi equals phi b, let's say, minus phi a. There I am. That's the height that I've climbed. Equals the path integral, the integral along the path of d phi, I guess, which equals the integral along the path of, let's get it right, di phi by di x1 dx1 plus di phi by di x2 dx2. You see how I've casually decomposed d phi here into its two components and then integrated with respect to them. The integral along the path of di phi by di xi dxi summed over I. See how valuable and interesting and instructive Einstein's summation convention is. Notice how this argument here does not depend upon the fact, well, it works for Cartesian coordinates, of course, but it doesn't care that the coordinate system is a little bit wobbly. It might do if there might be issues if I've got global topology issues, if I'm working on the surface of a torus or something. But basically, this is a pretty good way of thinking. I'm going to develop this because we need to know this. We need to know about curvature. So where do I go? I'm going to say that the path is xi equals xi, which depends on a value of lambda, and lambda marks progress along the path. Okay, So that is my definition of my path. That is my definition. I guess you could say P maps lambda is mapped to xi. Yeah, you can. Yeah. Well, there it's just a path. All right. So what happens to my little formula here? Well, yeah. What have I got? I've got the integral along the path of di phi by di x1 dx1 plus. Actually, I'll leave that there. Di phi di x2 di x2. And now I'm going to make the observation that xi is itself a function of path of the path parameter lambda. That's delta phi. The integral from lambda equals 0 to 1 di phi di x1 di that's an x1 by di lambda d lambda, and this is along the path, plus di phi di x1, oh no, that's a 2 now, di x2 di lambda di lambda. So now you'll see we've got the same lambda differential in either one of them, and we can just take that factor out. Lambda equals, I say 0 to 1, doesn't matter, we can call it what we like, it just changes this, it just changes the differential and the infinitesimal at the same time. So it's d lambda times di phi di xi di lambda. Notice the implicit summation over I. Yeah. What we want, if I'm calculating this, is for the altitude which I gain from going to A to B to be independent of the path. So I might walk in some crazy path there. I've still gained the same amount of altitude. If I'm walking, it doesn't matter what path it is, I want this change, delta phi, to be path independent. And it's kind of obvious in the case of altitude, because you say, well, I'm at altitude 104 meters, and that guy over there is at altitude, person B is at altitude 110. So I'm 104, he's 110. I'm going to gain 6 meters altitude whichever way I go. Path independence. We want this. Oops, I'm in green. We want this delta phi, what did I call it? Delta phi. We want delta phi to be path independent. We want it to be path independent. So what I'm going to do, this has gone on too long already. Next screencast, what I'm going to do is I'm going to show what path independence is for a scalar. And the one after that, I'm going to start talking about path independence for transporting a vector field rather than a scalar field. Okay, I'm going to stop there. Stop.